Extreme physics.
This is the 2019 AP Physics C Mechanics Free Response questions. 2019, 1 through 3. In an experiment, students used video analysis to track the motion of an object falling vertically through a fluid in a glass cylinder. The object of mass m equals 12 grams. I'm going to write that down, but I'm going to put it in standard units. 12 grams is 0.012 kilograms. Is released from rest. All right? From rest. V initial equals 0. Top of a fluid column is shown above. The data for the speed of the falling object is a function of time. A graph in the grid below. The dashed curve represents the best fit chosen by students of this data. All right, so we got a velocity versus time. Right off the bat, we should think about what can we get from a velocity versus time graph. And, kind of look like that. What can we get from that? Well, from the slope, it always gives us information. Well, not always, but in this case it does. Slope is dv dt. We remember that from calculus class, and that is acceleration. The rate of change of velocity is the acceleration of the object. All right, so we can get the acceleration from that. Let's review position versus time. We don't have that, but if we did, it looks like whatever. What's the slope of that equal? Slope equals dy dt, which is the velocity. And if we had acceleration versus time, the slope of acceleration versus time is called jerk. We're not going to study that in this class. It's the rate of change of acceleration. But if we had something, we had some sort of acceleration, whatever it is, doesn't matter what it looks like. If we knew the function from here to here, if we found the area under the acceleration versus time graph, we should know what that represents. That's the integral a dt. What does that equal? Change in velocity, right? Change in velocity. Not velocity. That's where people run into problems. They say velocity equals the integral of a dt. No, it does not. It's the change in velocity between like t0 and t1, right? And if we were to take an integral of a time interval here, the integral of v dt, of course, is the displacement. In this case, delta y. Not the position, the displacement. If we know the final position, we can figure, or if we know the initial position, we can figure out what the final position is. And then, all right. And, all right, so know that all that good stuff. And that's important kinematics to know. But right now, I'm going to erase. We don't have these grades. We only have the velocity versus time. In fact, we don't even have velocity versus time. They said it's the speed. They said it was this speed. Right? They said it was the speed. Now, if this was velocity, right? If this was velocity versus time, in the way I do it, I always make downward negative. So if I was plotting velocity versus time, it would be more like that for this particular problem. But this is not velocity versus time. This is speed, right? So technically, we kind of can't directly find the acceleration from the graph because you need velocity versus time. But we can work with this. Does the speed of the object increase or decrease or stay the same? All right, and we had something like this. Doesn't flatten out, it's still going up. All right, well, is this speed increasing, decreasing, or staying the same? Well, at 0, it's not moving at all. And then later, it's higher, looks like speed's increasing. And then later, it's higher, looks like it's increasing. And later, it's higher, it looks like the speed's always increasing. And it increases, all right? In a brief statement, describe the direction of the object's acceleration and how the magnitude of this acceleration changed as the object fell. All right, well, so we had an object falling at a velocity like that, and So since they plotted speed, we can't directly get the acceleration from this graph. We're going to have some sign problems. So in this case, if we could look at this as velocity if we call down positive. Right? If we say down is positive, then we could treat this as a velocity versus time graph. And we know that the slope of a velocity versus time graph is acceleration. Right? So in this case, let's see, I need a ruler or something. Here's a ruler. So we can see the slope of this thing keeps getting less and less and less as we go up. So the slope is decreasing. Right? What was the question? Describe the direction of the acceleration. All right, the acceleration is always, it's getting less and less and less. In this case, it'd be a positive acceleration that's getting less, and positive is downward. So, in a brief statement, the object's acceleration is decreasing. The acceleration is decreasing. It's becoming less and less and less. It looks like it's going to get to the point where it's going to be flat and it's going to be going a constant velocity, but it's not there yet. All right. So object's acceleration is decreasing and it's downward. Object's acceleration is downward. That's a downward acceleration. Downward acceleration, and it's a decreasing acceleration. But the velocity is increasing. It keeps going up. It's just at the rate it goes up is becoming less with time due to the drag with the fluid. Using the graph, calculate the approximate value for the magnitude of the acceleration of the object at t equals 0.2 seconds. All right, well, I'm not going to do it on the board because you really got to do it with the paper and pencil. So I'm going to pop something up here, video afterwards. I don't even know where it's either going to be here or here. I don't know. But let me just talk about the idea of what we're going to do is if this was, what did they say, 0.2 seconds? Whatever. If this was the time we were interested in, we wanted to know the acceleration at that point in time. All I'd do is I'd take my pencil, right, and I'd put it right at the point in time that I'm interested in this case. Then I'd take my ruler and I'd pivot. I'm going to go backwards so it slides easier. The cork is kind of sticky. And I would slide it and move it around until it was tangent, and then I would draw the tangent line, and it doesn't look like it's drawing at all. This isn't even drawing at all. Let's get rid of that one. That looks like it's drawing. So then I would just go like, oh, and I moved my marker. The wheels are coming off, ladies and gentlemen, right? So anyways, I'd draw my tangent line, something like that, and I'd find 2 points on that tangent line and calculate the slope, because slope, in this case, would be delta V over delta T, and I would just find that. The students use the equation V equals that. All right, let's write that down. We're going to need this. I can tell right away. V equals, oh, it's a bad, I don't like that one very much. V equals A 1 minus E to the BT. To model the speed of the falling object and find the best fit coefficients to be 1.18 meters per second, and B is 1 over seconds. Use the above equation. Derive an expression for the magnitude of the vertical displacement. We want Y. What is the magnitude of the vertical displacement of the falling object as a function of time? All right. Well, we know that delta Y, and I guess that's position 0. So we know that delta Y equals integral of V dt. Right? And I guess, okay, so that's starting at position 0. So therefore, Y of t, because we had Y of t, delta Y is Y of t minus y0, which is 0, equals integral of a 1 minus e to the b negative bt dt. All right. Yeah, I don't need that. Now I'm going to start sliding stuff over here because I think I crammed myself too far off to the right. So y of t, is going to be the integral 0 to t a dt minus the integral a e to the minus bt dt. All right, I'm smelling a u substitution there. Let's do that. I'm going to do that. Let's let u equal minus bt. So that way we can get just a nice integral of e to the one thing, and it makes it easy. So we got du dt equals minus b. So therefore dt equals du over b. That's negative. All right, let's try that again. Oh, d is 0 to t. So this is a. I'll take the a out, and we're going to the integral of dt is just t. So that's what that one's going to be. Minus, let's do our u substitution. When t is 0, u is 0. When t is t, u is minus bt. And then we just end up with, bring the a out, and we end up with e to the u, right? That's e to the minus bt is the u, and then dt is minus du over b. All right, that's a little awkward writing it like that, but that's perfectly fine mathematically. All right, so this is this one is a times t minus 0 minus a plus a. We got a minus and a minus. I'm going to take out the b. A over b, right? We had the a, we're going to break out the b. And we had the integral of, we just had the integral of eu du. So that's just going to be e to the u. 0 minus bt. All right. So what do we end up with? AT plus a over b e to the minus bt minus 1. Right? E to 0 is 1. All right. Let's see, do the units work out? A was in meters per second times seconds would be meters, and that's what we're looking for. And A was in meters per second divided by 1 over seconds would be meters again. And unitless, unitless. Okay, units work. All right, hopefully that's right. There we go. Here's their answer. And we could plug our numbers in, I guess. What'd they want? Derive an expression. I guess we should put the numbers in. I'll leave that to you. You can check the answer too, because that's online. So plug your numbers in for A and all that stuff. And anyway, I'll write that down here just in case we need it. I don't know if we're going to need it later. Y equals AT plus A over B e to the minus BT minus 1. All right. So there we go. Derive an expression for the magnitude of the net force. Whenever they talk about net force, I always think of my favorite guy, Sir Isaac Newton.
I'm the
and his
dude.
second law. And what does a net force do? Well, it causes acceleration. That's the second law. And so whenever they talk about force, especially if they've given me kinematics information, I go, oh, I bet that relates to acceleration. So let's see. Whenever they say force, you got to be thinking, oh, acceleration. Acceleration. They said force. There must be an acceleration. If there's an unbalanced force. Find the magnitude of the net force. All right, well, they gave us velocity. Velocity equals a1 minus e to the minus bt. So I want acceleration because I know that F net equals mass times acceleration. Let's find that. So acceleration equals dv dt. So this is just a, which is a constant, so that's not going to contribute at all. So we end up with minus a, and then we're going to go minus b, so that's plus, and then e to the minus bt. Right? So there we go. So the integral, or the derivative of this is be ab e to the minus bt. And but that's what they want, the net force. So F net equals mab e to the minus bt. There's the net force. And then do we need to derive an expression for the magnitude of the net force? There it is. If we had to plug numbers in, we would just put in 0.012 kilograms. Make sure if you're doing a calculation, you plug the numbers in first. Make sure you show the grader doing your test that you know what these numbers are, because you could easily just plug the wrong number in, get a squirrely number, and they have no idea what you did, and you could lose additional points. 5t. So you had something like that. So you would just calculate that. F net t. All right. So there you go. I'm going to write that down. F net equals mab e to the minus bt. The students repeat the experiment with a taller glass cylinder that is filled with the same fluid. No. The cylinder is tall enough so the object reaches a constant speed. Well, you know what height you could guarantee that it was tall enough? That would be an infinite height. That definitely would be tall enough. Determine the constant speed of the object. All right. So if it's a constant speed, I know when that occurs. All right, I got a velocity function, and it keeps slowing down from the drag, and it eventually reaches terminal velocity. And that terminal velocity, you know when it definitely occurs? It occurs when time equals infinity. If that thing's going forever, if it's going to reach terminal velocity, it's going to make it there by infinity. So I'm going to put a time equals infinity in there and see what velocity I get. That's as fast as it's going to go. So let me just rewrite this so it's just easier for my simple brain to understand. Minus e to the, all right, now that means it's just a fraction, so that's e to the bt, right? All right, so when that becomes infinity, this number becomes really big. 1 over a really big number is 0, so that becomes 0 when t equals infinity. So therefore, v equals a1 minus 0, which is just a. All right, so that's the terminal velocity. Terminal velocity is a meters per second. I guess 1.18 meters per second is the terminal velocity. And that's when it hits constant speed. Constant speed. Terminal velocity means it's not going to go any faster. And determine the force required for the fluid at the time of this. Well, I've been studying physics for quite a while, and I know that when something's going constant speed, or in this case, constant speed in a straight line down, that means constant velocity. And if it's in constant velocity, I know that the net force is 0, because Sir Isaac Newton said, I'm the dude. Net force equals mass times acceleration. Well, but if it's a constant velocity, the acceleration is 0. So the sum of the forces is 0. Let's take a look at our object. So we're looking for when the sum of the forces equals 0. So we got our object, and it's falling through a liquid like that. And I got to circle the object of interest. I got to draw myself a free body diagram. Here's y, here's x. Here's my object. All right, so we got the drag force up, which they just called F. And we got the weight down. They must be equal. If it's a constant speed, constant velocity, in this case downward. So I end up with F minus mg equals 0. I got one force up, one force down. So the force equals the weight. The drag force equals the weight in this case, which I guess is 0.012 kilograms times 9.8 newtons per kilogram. Right, whatever that is. That's looking like it's about 0.1 something newtons. Whatever value that is. That's how you do that one. The force exerted by the fluid is at this time. How do I justify it? Newton's second law. Newton's second law. If it's constant velocity, I would say it's moving at constant velocity. Therefore, all the forces are balanced. So the upward force of drag must equal the downward force of weight. So the drag force equals the weight, and there you go. Beauty. Is that it? I guess I'm done. This is problem number 2 from 2019. A pendulum of length L consists of block 1 of mass 3m attached to the end of a string. Block 1 is released from rest with the spring horizontal as shown above. At the bottom of the swing, block 1 collides with block 2 of mass m, which is initially at rest at the edge of the table of height 2L. Block 1 never touches the table. As a result of the collision, block 2 is launched horizontally from the table, landing on the floor a distance 4L from the base of the table. After the collision, block 1 continues forward and swings up. At its highest point, the string makes an angle theta max. With the vertical, air resistance and friction is negligible. Express all algebraic answers in terms of ML and physical constants as appropriate. All right. This looks like we got a situation. This is a pretty typical problem where you're going to need to know when can I use which conservation laws. We're going to be using conservation laws. We're going to be using, let's say, kinematics equations, projectile motion. All right, so we got something like this. So this is block 1. And it's got a mass of 3m. It's going to swing down. And it's going to hit. Here's my 1. And it's going to hit 2. Which is a little bit taller. It's not going to hit the table. Here's my table. I'm going to make it a short table so I have room to work. So this is 2L. I know it's not drawn to scale, but I need the room. I got a small board. And then it goes, it's 2L. And then it goes a distance 4L. All right. Let's get a land there. We got a projectile. Travels parabolically. And then after that, this swings up. I know that's not quite right either. This swings up to an angle theta. So this goes up to theta max. Theta max. All right. Now, in this problem, from here to here, we got something swinging a pendulum, so mechanical energy is conserved. From here to here, mechanical energy is conserved. Now, when they hit, when they're slamming together, mechanical energy is probably not going to be conserved. Didn't say it was an elastic collision. It's highly unlikely that it is. But momentum is always conserved in a situation. This is a closed, isolated system. And at least during the collision, we can use the impulse approximation, even if there is a little friction with the table. I'm going to label some points in time here. We're going to start at 0. And then this point is 1 and 2. 1 is right before they hit, and 2 is right after they hit, but they're basically the same position. And then 3 is when it's at its maximum height. And I don't know, I guess we'll call this 4 when it lands on the ground. We don't really know that relationship there. So we'll call that 4. I don't know which one hits first. I don't think it's going to be important. All right. So now the important idea though here is that that's easy to understand. 0. 1 is right before collision. Right before the collision. 2, right after collision. All right, so right before, right after. There is essentially no time difference between these. It's basically the same time and no significant position change. But anyways, all right, so there we go. So let's take a look at what we got. And I guess this is mass 3m. I'll write that there. This is mass 3m, and this is m. Right? Yeah. Where? All right. Determine the speed of block 1 at the bottom of the swing just before it makes contact with speed. All right. So we want to know, right before it makes contact, we want to know V1 equals. In my world, right? Make sure you label these. Okay, what's V1? All right, we're going to use, from here to here, I'm just going to use conservation of energy. I'm going to say the energy at 0 equals the energy at 1, and mechanical energy is conserved. In this problem, we only have gravitational potential energy and kinetic energy. Oh, I will say gravitational potential energy is 0 here. So in this case, we only have gravitational potential energy, right? It has height, but it's not moving. So gravitational potential energy only. And then when it gets down here, we said that 0 position. So we're going to say kinetic energy at 1. The gravitational potential energy is 0 because kinetic energy at 1. So what do we have? 3mg L, right? Is that L? Yeah, that's L. This is L. All right. 3mgl, right? The mass, which is 3m times g times the height, equals 1/2 3m v1 squared. Boop, boop. What do we got? It looks like v1 equals the square root of 2gl, right? So that's the speed right there. v1 equals, I'm going to write it right up here. v1 equals the square root of 2gl. Probably going to need that. What do we have? Speed of the blood. Do we have to put numbers in? No, I don't think we can because we don't have any numbers to put in. All right. Beauty. Good. I don't like putting numbers in. So we had this thing swinging down. I have a prop. I got a string swinging down. And here we go. We got it swinging down. Like that. All right. Now, if you notice, as it's swinging down, sucker's in circular motion. That's going to be an important idea here. That's in circular motion. So on the dot, which represents block 1, draw and label all the forces, not components, that act on block 1 just before it makes contact with block 2. So we're looking at time 1. What does that look like? All right, so what do we got here? We got y and x. This thing is in circular motion. Boom, like that. And in fact, when it gets to the bottom, it's actually in uniform circular motion. It's neither speeding up nor slowing down. Just at this point, it's in uniform circular motion. Now, when it's out here, where did it go? I lost it. Here it is. Right? When it's down here, it's in uniform circular motion. Right? Because it has a net force towards the center of the circle. But on the other hand, when it's here, it is not in uniform circular motion. It's actually speeding. Like at this point, it's not speeding up or slowing down because there's no force this way or this way. Now when it's here, it is speeding up, right? Because the opponent of gravity is this way. So only at the bottom, right here, it's going to be in uniform circular motion. Not that uniform is going to be important in this problem, but it might be some other time. So here we go. We got our forces on here. I got my thing. Here's my block. I'm going to circle the object of interest. There's only one thing in contact with it, and that is a string, and that's applying a tension force. I'm going to call that T, and it also has weight. Now, this thing is accelerating, And in fact, since it's in uniform circular motion, I'm going to not use I'm going to actually use my RTZ coordinate system. This will be R, which is towards the center of the circle. This would be T, like that. And this also has weight, but the weight has to be smaller. This is accelerating towards the center of the circle. It has an acceleration towards it. It's not accelerating that way or that way, but it is accelerating that way because it's turning, right? So that's what our free body diagram should look like. You got your force of tension towards the center of the circle, which I'm calling the R-axis, and we got the weight. All right, so there's our, and you draw it on the little grid that they had there. All right. Each force must be represented by distinct arrows starting on and pointing away from the dot. Forces with greater magnitude should be represented by longer vectors. All right, and I made that one longer because it's accelerating that way. All right, drive an expression for the tension force. So they're calling it F of T. I just called it T. And the string, when the string is vertical, just before block 1 makes contact with block 2. All right, so we're looking at time 1 again. If you need to draw anything other than to assist you, but use the space below. Do not add anything to the figure there. Well, I didn't use the figure anyway because I didn't have it. All right, so I need F of T. All right, well, let's take a look. Let's apply Newton's second law. I want to know what that tension force is. Well, the sum of the forces in the R direction equals mass times the radial acceleration. This has a radial acceleration. It's in uniform circular motion, and even if it wasn't uniform, it is in circular motion, so it has a radial acceleration. And you need to, so we have the tension up. I'm going to call that positive, minus the weight equals m, and the radial acceleration is v squared over r. Make sure you know those relationships, right? You know the radial acceleration is v squared over r, or omega squared r. Either one, in this case, v squared over r is more convenient because we're solving for v. But r is L. I'm going to say L. M is actually 3m is the value. So let's put the values in. 3m over L. And we'll put 3m here too. 3m. 3mg, because that's its mass. So the tension equals 3mg plus v squared over L. All right. So I guess that's what they're looking for. They wanted to call it, so I would, since they're calling it that, I would put it in the terms that they wanted. F of T. And let's see. I don't think V's allowed, is it? V's not allowed. V's not, but luckily we got it. That's V1. That's V1. That's not allowed. So let's go 3mg plus V1 squared would be 2gl divided by L. Right? So V1 is that. V1 squared is just 2gl. And then what do we got? 3g, 9, what? We got 3 times 3 is 9. 9mg. All right. Ft equals 9mg. All right. Yeah, that's why it's hard when you're swinging down on a rope like that. It's hard to hang on at the bottom because look at the force. The force gets big.
Hold on really tight.
Oh. What else do we need to do here? All right, then they gave us L. Why did they give us L? Why do we? I don't want to calculate anything. Calculate the time between the instant the block leaves the table and the instant it hits the floor. That looks pretty straightforward. It looks like we have we got a projectile launched horizontally. Therefore, it has no initial vertical velocity. So we just want to figure out how long does it take for something to drop a height to L, right? And this is under constant acceleration, so we can use the kinematics equations. Let's see. Let's use this one. Let's use El Grande. Delta y equals V0 delta t plus 1/2 a delta t squared. We'll use that one. And in the y direction, this is only in y. I should put my y's here. So initial velocity in the y direction is 0. It's launched horizontally. It has a horizontal velocity, but we're not looking at that. We're breaking it into its x and y components. So what do we got? Delta y is 2L. 2L equals 1/2 g delta t squared. And we want to just know what t is, right? So what do we got? We got 4L over g square root equals. And since t starts at 0, that is t. Calculate the time. So there we go. So t from 2 to 4, from here to here, is square root of 4L over g. Calculate the speed of block 2 as it leaves the table. Well, we knew the speed of block 1, and they hit and it flew off. We know momentum's conserved, but the thing is here, we could just figure out how fast it's going because, we got a projectile that went horizontally. We know how long it was in the air, and we know it's going to go at constant velocity. So we could figure out, and we know how far it travels. The velocity in the x direction equals delta x over delta t, right? That's average velocity. Velocity is going to be constant horizontally because there are no horizontal forces. That's true with our projectiles in general. Constant velocity because there are no horizontal forces.
I'm the dude.
Constant acceleration because we have an unbalanced force.
I'm the dude.
Of the object's weight. So delta x, what do we got? 4L is delta x. And delta t is square root of 4L over g is the velocity. I guess they probably want me to put numbers in. T equals 0.55 seconds. It's 5.45 meters per second. So that would be, I should start labeling these. Calculate the speed of the block just after it collides with block 2. So when they collide, it's highly unlikely that kinetic energy is conserved. But I know momentum's conserved. This is a closed, isolated system. So I'm going to say that the momentum, the system is 0. Oops, not 0. 1 equals the momentum of the system at 2. So the momentum of the system at 1 is just the mass of this thing times its velocity. So 3m times the velocity at 1, which is the square root of 2gl. So we have the velocity of this. So the momentum of this thing is 3m is its mass times its velocity of the, what do they call that? The block. I'm going to call it b. That's the block. Velocity of b at 2. Plus the momentum of this thing, which is mass m, right? Times the velocity there. What are they calling that thing? There's block 1 and block 2. All right. B1, and then this is mass times velocity of B2 at 2. So this is what we want. So what do we got? We got 3m square root 2gl minus m V2 of block 2, which is, I guess, I got to use numbers now. I hate using numbers. 5.45 meters per second equals, velocity block 1 at 2 and divided by 3m. All right, our m's can go away like that. And what do we got? 3 times the square root of 2 times 9.8 meters per second squared times L, which is 0.75 meters, minus 5.45 meters per second divided by 3. Yeah, 2.02 meters per second. All right. Velocity of block 1 at 2 times 2 equals 2.02 meters per second. Calculate theta max that the string makes with the vertical as shown in the figure. All right. So from here to here, If we know how fast this is going, this thing flies off. We can use conservation of mechanical energy here. Mechanical energy is conserved between time 2 and time 3. That's just a pendulum swinging up. Mechanical energy is conserved. There are nothing but conservative forces acting on our pendulum. To get that angle, we need to do a little analysis. It's going to be easy to figure out how high it goes, but we just need to. We're going to need to relate that to an angle, right? So we're going to have to use this old trick, where this thing is here, and then it goes up to here, like that, and we want to know what this height is. It's going to gain gravitational potential energy, lose its kinetic energy. So if I draw this straight across like this. This is theta right here. I want to know h. Well, I'm going to put in a temporary variable, which I will just I'll call it y sub theta. And the thing we have to realize is this length L is y sub theta plus h. And I really want to know what h is. I'm going to want to know how high this thing went. So I'm going to say, okay, h equals L minus y sub theta. But what is y sub theta, right? That is the adjacent side of this right triangle right here, which is just going to be L cosine of theta. So h equals L minus L cosine of theta, like that. All right, that's going to be useful to us because doing the conservation of energy is not going to be difficult. So the energy, and this is for block 1, energy at time 2 equals the energy at time 3. So at 2, this only has kinetic energy. So the kinetic energy at 2 equals the gravitational potential energy at 3. And so the kinetic energy at 2 is 1/2 its mass, which is 3m v2 squared equals 3m g. I'll call that h, right? Call that h for now. Let's get rid of the masses, and we're gonna put in our v2, our vb. Block 1 at 2 is 2.02 meters per second. We're going to put that in there in a second. But let's do this. Let's go 2.02 meters per second. We're going to square that, divide that by 2, and divide that by 9.8 meters per second squared, just bringing g over here, equals h. But h is L minus L cosine of theta. Right? I brought the g over, and what was left was h, but h is L minus L cosine of theta. So all I really need to do now is solve this for theta. Kind of getting run out of room. I'm going to put a line here to demarc. Drawing a line on the board. So we ended up with, so I got L cosine of theta equals L minus 2.02 meters per second squared divided by 2 times 9.81 meters per second squared. Gotta draw another line like that. Otherwise we're going to get confused. Theta is going to equal, I'll plug my numbers in now, I guess. And what I do, I'm going to divide that by 0.75 meters. And this is going to be the inverse cosine. All right. Really running out of room. I wish I had a bigger board. So theta equals the cosine, inverse cosine of all this stuff. Theta equals 43.7 degrees. I got 43.7 degrees, 44 degrees, something like that. so this is question 3 for the 2019 exam. A horizontal circular platform with rotational inertia IP, I guess P for platform, rotates freely without friction on a vertical axis. A small motor-driven wheel that is used to rotate the platform is mounted underneath the platform and touches it. The wheel has radius R, all right, and touches the platform a distance d from the vertical axis of the platform as shown above. The platform starts from rest. All right, I'm going to write that down so I don't forget. So it starts from rest, so omega 0 equals 0. And the wheel exerts a constant horizontal force of magnitude F tangent to the wheel until the platform reaches an angular velocity omega p. All right. So I guess that's the final velocity after time delta t. All right, delta t. The wheel stays in contact with the platform without slipping. Okay, so what's happening, and hopefully this will be big enough for you to see. I may have to do an insert later. We'll see. So we got this thing, and we got a wheel underneath it, and it is spinning, and the spinning of this wheel is it's actually turning the other way, isn't it? Let's see. So the back was going like that. Yeah, no, it was like this. Okay, so it's spinning like this, and what's happening is this lower wheel is applying a constant force that way, causing this thing to causing it to rotate. Drive an expression for the angular speed omega p of the platform. Express your answer in terms of IP, R, D, F, delta T, physical constants as appropriate. Okay, again, be appropriate. Don't be inappropriate on this exam. They'll kick you out. All right. So, they said it was a constant force. Therefore, it is also a constant torque. We're talking about rotation. So we're going to accelerate this thing up to omega p in a time delta t. So, all right. So let's see how to draw this thing. I'm going to draw it from a side view like that. And I'm going to have the disc here. And it's rotating like that. Right? So it's rotating like that. And then that's causing this to go around like this. So this front of the wheel is going that way, right? So we're looking at this from the side angle. They gave you a perspective just so you could see what's going on. So now we're going to be looking direct straight on like this is the way I drew it, like that. And all right, so it's going to turn like that. So now this is kind of like the velocity of the hub that I'm showing here. You know, it's going around like that. And drive an expression for the angular speed omega p. Now, this is going to start at rest and go to here. They said the force is constant. There's a force being applied to this wheel. Let me get rid of this just because we're in a space. There's a force being applied to this wheel like that. There's a force, so that's applying a torque. So this is our side view. Let's take a look at a bottom view. Here's our big wheel, like that. And we have the little wheel. From the bottom, looks like a rectangle. It's like that. And so this thing is applying a torque because it's applying a force. There's that F force, right? That's applying a force F. And relative to the center, this is D. So this is applying a torque, force F, R cross F, right? You know, this is D is actually like, this is our R vector right there, our position vector. So it's a constant force, therefore it's a constant torque. And we're going to apply Newton's second law of rotation.
I'm the dude.
Sum of the torques equal I alpha. Like that. And we only have one torque on it. It's this thing. It's FD. Actually, if we look from the top, which is the view they have, I mean, here it's looking like a negative torque, but from the top it would look like a positive torque. So let's make this positive, right? If we're looking from the top, which is the way this was drawn in here, that is a positive torque equals FD equals moment of inertia, which is I of the platform alpha. So FD over I platform equals the angular acceleration. And since it's a constant force, it's a constant net torque, we can use our kinematics equations. I think we're going to use omega P equals omega 0 plus alpha delta T. And they gave us delta T. All right, beauty. So omega P, this is 0, equals alpha, which is FD IP delta T. Right? All right. Yep. There's our answer, I guess. All right. So now the only reason we were able to do that is because this was constant angular acceleration. Why? Because the force was constant. It said right there somewhere, force of magnitude F, constant horizontal force of magnitude F tangent to the wheel, right? And they said it was in that direction, so it's a right angle, so we just take F and multiply by D because F and D are at right angles. All we need to do is multiply those to get the magnitude of the torque. Determine an expression for the kinetic energy of the platform at the moment it reaches omega P. It sounds like they're leading us into something. Why are they asking about kinetic energy? Sounds like they're leading us down a path. Maybe they are, maybe they are. Kinetic energy. This is K rot. Equals 1/2 I omega squared. Equals 1/2 I of the platform. FD over IP delta T squared. Guess we could simplify that a little bit because that's going to be squared. That's not. Bring that and one of them cancel. And we get something like that. All right. Conceptually not a difficult problem at all, I don't think. You had to kind of see what was going on with the... you had to understand what the layout of the thing was, but other than that, so far nothing tricky's going on. Actually, I should make sure I have all this stuff here. Yeah, I'm good. IPR, yeah. All right. Drive an expression for the angular speed of the wheel. That's the wheel. When the platform has reached the angular speed omega p. Express your answers in terms of dr, omega p, and physical constants. Now, one thing we have to realize, what is the same between these two? Their angular speeds are not. Because the wheels are different sizes, they're going to go at different speeds. Right? The angular speed of the little wheel is going to be higher than the angular speed of the big wheel. But what is the same, because they're not slipping, is the speed of this rim, just the edge of the rim of the wheel, is going to be the same as the speed of the platform at the point of contact. Only at the point of contact, which isn't quite the rim. It's inward a little bit. So you have to realize that the speed of this outer wheel is the same as the speed of this point on the wheel. They are not slipping relative to each other, so they're moving at the same speed. If we take a look at this, the speed anywhere along the platform here equals the speed of this outer portion of the wheel. So that's the key here. We had to see that. The speed of the platform equals omega platform times d. Right? speed equals omega r, right? So we're interested in that position D. And the velocity of the wheel equals omega of the wheel times r. All right? But these two are equal. These two are equal. So omega p d equals omega, not omega. Name so good we named it twice. That's not omega. It's not omega. It's omega w. Wheel r. All right. And we want to know what is omega w. All right. So omega w is omega p d over r. All right. Hopefully that's right. All right. When the platform is spinning at angular speed omega p, the motor-driven wheel is removed. All right, that's going away. We're not going to have that anymore. You can kiss the wheel goodbye. You're on your own now, buddy. You're spinning. Your inertia. Let's get rid of that. We don't have any forces from that anymore. Spinning. You're relying on inertia now. Inertia's taking over. Spinning. A student holds a disc directly above the and a concentric platform as shown above. All right. I bet they're going to drop it. The disc has the same rotational inertia IP as the platform. All right. So they're kind of identical discs. The student releases the disc from rest and the disc falls onto the platform. After a short time, the disc and the platform are observed to be rotating together at angular speed omega f. All right. Derive an expression for omega f. Express your answer in terms of omega p, IP, and physical constants as appropriate. You always want to remain appropriate. All right. Time to erase. All right. This screams conservation of angular momentum. Our system is going to be this wheel on a frictionless bearing and the one dropped on top of it. They're identical. That is a system. The system itself has no net torque. So since there's no net torque on the system, angular momentum is conserved. All right. So 0 times 0 is before they come together. And time 1, I'm going to draw a little smaller, is when they're together and spinning together. There's no more slipping. When they hit, they're going to slip a little bit for a little while, and then they're going to stop. Okay? So, mechanical energy is not going to be conserved here, right? This is an inelastic collision, but angular momentum will be because there's no net torque on the system, right? This one will apply torque to this one, to the bottom one. The top one will apply torque to the bottom one, and the bottom will apply torque to the top one. But since they're all in the same system, it's an internal torque, and we don't care. It's external torques outside the system that we can't deal with. All right? So angular momentum of 0 equals angular momentum of 1, right? All right, so we started off with IP, I the platform, I omega. Oh, what was that called? That was called omega p, right? The initial was omega p before we dropped it. And then that is going to equal the angular momentum of both of them, which is going to be, they're going to have 2IP, and that's going to be omega f, I guess they're calling it. Omega f is what we're looking for. Well, this isn't too bad. So omega f equals omega p over 2. Well, so far, it's been pretty straightforward, I think. All right. A student now uses a rotating platform. Oh man, why do they keep giving me numbers? They now give me the rotating kilogram meters square. Student uses the rotating platform to determine the rotational inertia IU of an unknown object about a vertical axis that passes through the object's center of mass. The platform is rotating at an initial angular speed, omega initial, when the unknown object is dropped with its center directly above the center of the platform. The platform and the object are observed to be rotating together with an angular speed omega f. The trials are repeated for different values of omega initial. A graph of omega final as a function of omega initial is shown on the axis below. All right. It looks like we're going to draw a line of best fit, and we're going to be interested in the slope, if you ask me. That's what it's looking like. It looks linear. On the graph of the previous page, draw a best fit line. Hey! Nailed it. Nailed it. Right? So we're going to draw a line of best fit. I'm sure you can do that. I'll do an insert of that. It doesn't make sense to try and do that on the board. Using the straight line, calculate the rotational inertia of the unknown object, IU, about a vertical axis pointer. All right, we have ourselves a graph. Got ourselves a linear graph. Looks like this. And we got omega final and omega initial. And then we're going to have some sort of linear fit like that we're going to be able to find the slope of. And we want to find what is, we had a disk. This one had, this was IP, and this had IU, I unknown. And we want to know what that is. And we're going to use our line of best fit. All right, I think we're going to use conservation of angular momentum again. So we're going to say that the angular momentum before equals the angular momentum afterwards. And beforehand, we had IP omega initial. That's the angular momentum before. That's the only thing. And then we drop this thing on top of it. IP omega final plus I unknown omega final. Right? So angular momentum before equals angular momentum afterwards. So, of course, we could just simplify this. We could factor out the omega. So we get IP plus IU omega final IP omega initial. So I'm going to get this in the form of y equals mx plus b. Let's try that. See if that works. Well, that's our y variable. So, all right. So I guess omega final equals IP omega initial all divided by IP plus I. I could just rewrite this as IP plus IU omega initial, right? Where this is the slope. Right? There's the slope. So this is y, boop, equals m. Slope is IP divided by IP plus IU, omega initial. So all we need to do is we're going to go slope equals IP over IP plus IU. Right? So therefore, just rearranging this, I could say that IP plus I unknown equals IP over slope. So therefore, I unknown equals IP over slope minus IP. All right. All right. So that should work out for us. There may be other ways to do it. That's one way to do it. That's one way to do it. So I just need to get the slope value, and they gave me the IP value, and we could go from there. I'm just going to use the numbers that the College Board used for the slope. All right, let's see what that gives us. 4.1 kilogram meters squared. 4.1 kilogram meters squared. The kinetic energy of the spinning platform before the object is dropped is K initial. The total kinetic energy of the object platform system when it reaches angular speed omega f is kf. Which of the following is true? K final is less than whatever. All right. So this is definitely an inelastic collision. One's going to be sliding on the other, stuff like that. There's going to be thermal energy and stuff like that. So kinetic energy is not conserved. The kinetic energy initial is going to be greater than the kinetic energy final. So I guess that's the first one. K final is going to be less than K initial because this is in inelastic collision. When the two are dropped on each other, there's going to be this sliding. You get thermal energy while the sliding. Now, angular momentum is still conserved because there's no net torque on the system, but mechanical energy is not conserved. All right. Well, one of the students observes, I wonder which one. That inquisitive one, you know the one. Observes the center of mass of the object is not actually aligned with the axis of the platform. Is the experimental value obtained in part E greater than, less than, or equal to the actual value of the rotational inertia of the object about a vertical axis? All right, let's get into the question, right? So in the experiment, if we look at the top view, this is the thing that was dropped on there. It was off axis, right? I'm exaggerating, and I'm sure it wasn't that far off axis. So in the experiment, the value of IU, so this is the value we got. This is I unknown. It was off axis, right? It wouldn't have been that much, but let's make sure we're real clear to show that it's off axis. So this is what we measured. We dropped. This is what we did in the experiment. We actually measured the moment of inertia about this point, not the center, even though we thought it was the center. Is the experimental value of this greater than, less than, or equal to the actual value of the unknown object about it, a vertical axis passing through its center? So this would be the experimental. This is what we found experimentally, and compare that to this. IU, what did they call it? Actual value. All right, so I guess I gotta call it actual. All right, actual about its center. Which one's bigger? Let me just see the question. Is the experimental value greater than, less than, or equal to this, right? So, what do you think? Where are we always going to get the lowest moment of inertia on anything? Lowest moment of inertia, right? And it also answers the question, where is an object if it's free to rotate? If it's just, you throw it up in the air and it's free to rotate, about what point will it rotate? Well, it's going to rotate about its point of lowest rotational inertia, or moment of inertia. So remember, if we take an object like, I don't know, let me grab an object. All right, I'm looking for my big ruler and I don't know where it is. I can't find my big ruler. And so I'm going to use a broom. Now I know it's not symmetric. I wonder if I can take the end off. Yeah. Okay, that'll be better. I'm going to take the end off the broom. Right? So what's the rotational inertia of the broom? Right? Broom handle. What is it? Well, about what point? Because if I want the lowest rotational inertia, where am I going to rotate it? About its center, right? Okay, I can change its angular rotation most easily about its center. On the other hand, if I go about the end, right, doesn't even show the screen, I can't rotate it nearly as fast. This is going to have the highest rotational inertia because, remember, rotational inertia is the mass times the distance from the point of rotation squared. And in this case, we got a lot that's much farther away than we go in the center. Now everything's much closer, and the distance is really more important than the mass because it's the distance squared. So, oh, that wasn't good. Don't smash your microphone. Those things are expensive, right? So anyways, rotating about the center will always give the lowest rotational inertia if it's symmetric, right? As long as the mass is symmetric. So the center of mass, rotating about its center of mass is what I should have said. And the center of mass on that thing will be the center. The balance point is going to be the lowest moment of inertia, right? Farther out I go, it's higher moment of inertia, right? All right. Since it's not at the center, is going to be greater than that. So I guess it's the first one, greater than. Justify your answer? Well, I just justified it. I would say the moment of inertia is always lowest about the center of mass. Since this is not at the center of mass, it's going to have a higher moment of inertia. And you could even throw in the parallel axis theorem, right? So I equals I center of mass plus d squared m, right? So the moment of inertia is always going to be greater when you're not around the center of mass. So there you go. That was that one. I didn't think that one was that bad, really. Conceptually, there's a lot to it. You had to do a lot of stuff. They're making you do a lot of stuff these days. I didn't think it was that bad. All right, that was a 2019 exam. What a great year that was. That was before we had these viruses bouncing around that we knew about. So anyways, I'll catch you later.
It's Street Fair Zone.